Greetings everyone, my name is Farrell Liam and my student number is 21055310889. And today I'm going to present about machining process chapter A to chapter C. So my main reference from these topics is from the Handbook of Manufacturing Processes, How Products, Components and Materials Are Made by James G. Brala. So today I'm going to present about 3 chapters. The first one is lathe and other turning operations. The second one is round hole making methods, and the last one is grinding and abrasive machining. We go into the first one, lathe operations. Lathe operation produced with a cutting action, surfaces of rotation, both external and internal, in a workpiece. The workpiece is rotated in a lathe, screw machine or chucking machine. These machines are used extensively in the production of parts that contain surfaces of rotation. And these are the lathe operations. The process of the lathe. There's a turning, facing operation, chamfering operation, thread cutting operation, spinning, grooving, drilling operation, parting off or cutting, boring and knurling. And I'm going to explain all of those in the next slides. The first one is turning. Turning is the most prevalent lathe operation. In its common form, a single point cutting tool is moved on a precise path with respect to a rotating workpiece. When the tool moves parallel to the axis of rotation, straight turning takes place and the surface machined is cylindrical or part of a cylindrical. And these are the turning operation, where this is the workpiece and this is the tool. This is the video of the turning operation, where this is the workpiece and this is the tool. So that's how turning operation works. Now let's get into the next one, form turning. Form turning occurs when a single point cutting tool moves longitudinally in a path other than a straight line, or when a cutting tool ground to a particular curve or otherwise irregular edge is fed radially into the rotating workpiece. The next one is tracer turning. Tracer turning is a process for form turning. The inward and outward motions of the cutter as it moves longitudinally along the length of the part are controlled by the motion of a stylus as it bears against a template or master part. A variety of tracing mechanisms are available, powered hydraulically, pneumatically, or electrically. This is the illustration of the tracer turning. The next one is facing operation. Facing operation produces flat surfaces whose plane is at right angles to the axis of rotation of the part. As the part rotates in the lathe, the cutting tool moves radially toward the axis of rotation, removing material as it advances. The operation is used to produce flat surfaces on castings and other parts that usually also require turning or some other lathe operation. This is the workpiece and this is the tool. This is the example of the video. The next one is grooving operation. The cutting tool, usually ground to the width and bottom shape required, is fed into the work cutting a groove of the desired dimensions. Grooves can be cut into an external or internal surface that such a cutting tool can reach. This is the process of grooving operation.
Okay, right now I'm going to be setting up a grooving tool on the Produksi lathe. First thing I have to do is make sure that the tool itself is nice and straight, that it's not off at some angle. Alright, once we know that that's done, we have our tool locked down and we have to pick up the Z and the X. The first one I'm going to pick up is the Z. I'm going to go down in front of the face, the part that's already been faced. I'm going to use a piece of paper. This paper is just 4,000 7-inch thick. So I know that when I touch down on the edge of the part, that I will be 4 thousandths away on the Z. So I'm going to get really close with it and move the paper back and forth and go really slow on the Z until that it grabs the paper. And when it grabs the paper, I know I'm about 4 thousandths away. Okay, that still a little bit more. There we go, 4 thousandths away. So at this point, I'm going to set my Z to 0 on the control. So that's go Z0 absolute set on the control. I'm going to bring the tool back on the X, move down a little bit, and I'm also going to move into my X position now. So I'm going to use the paper again. I'm going to get really close before I put the paper in there, and then slowly approach the part on the diameter. I'm going to touch it off, and again, 4 thousandths away. Now the trick here is with the X is a little different. Since we're cutting on actually cutting on a radius, we have to double the amount of that thickness. So I have to say that it's 0.008 bigger than whatever the diameter is. Okay, that's something you got to remember. So I'm going to measure the diameter on that right now. I'm using a caliper, but you really should be using a micrometer. I've got 0.984. So I add 8 thousandths to 0.984, and I get 0.982. That's giving me my X. X 0.992. Absolute set. Okay, so this is how we position. X0 right now is back here. So if we zoom in, we can see that the tool at Z0 is right at the edge of the part there. Sorry for the jumpiness there. Alright, right at the edge of the part. A little blurry, but you can see where we are. Alright, now I want to position the tool for cutting. I'll cut a groove. Pull this back so I don't smash the tool into the diameter. I'm going to position the edge of the tool over 500 thousandths. So on the Z, negative 0.5. And then I'm going to turn my spindle on first before I plunge in. I'm going to plunge straight in on the X to cut the groove and then straight back out again. So this is how you do it. Make sure you feed it slowly. You don't want to go too fast, you'll break the tool bit. So you allow the tool to do some cutting. And again, I'm going straight in on the X. Straight in. I'm going to go to a diameter of this groove to 0.850. And then back straight out again.
So that's how the grooving operation works. The next one is knurling operation. Knurling operation is not really a machining operation because the knurl is formed, not cut, in the workpiece. Knurling is a common lathe operation. The hardened knurling tool rolls against the cylindrical surface of the rotating workpiece with high pressure, causing the surface material of the workpiece to flow into peaks and valleys according to the pattern of the knurling tool. The result is a surface part that roughened to a particular pattern. So this is the workpiece and this is the knurling tool. This is the result of the knurling operation. This is the video. This process is still a turning operation, not a knurling operation. And now he puts the knurling tool to do the knurling operation. He puts the lubricant into the workpiece. Now this is the result of the knurling operation. It forms a pattern in the workpiece. Next one is cutting off or parting. When parts are made in lathes and screw machines from bar stock, the final operation is to sever the part from the remaining bar material. This is accomplished by advancing the cut-off tool, a narrow grooving tool, radially into the work. This is the process of the cutting off operation. So that's how the cutting off works. The next one is engine lathes. Engine lathes are general purpose machines that provide the most basic means of performing turning, facing, grooving, knurling, and threading operations. These machines can also drill, ream, and bore holes at the center of rotation. The next one is turret lathe. Turret lathes differ from engine lathes in that they have a slide carrying a usually hexagonal tool holder, a turret, in place of the tailstock. This is the hexagonal tool holder. The turret can hold cutting tools in each of its sides and can be fed longitudinally and on some machines transversely. Turret lathes are particularly suited for moderate production levels when automatic screw or chucking machines may not be justifiable. This is the turret lathes, and this is the hexagonal tool holder. Okay, we go into the next one. Screw machines. Screw machines are automatic lathes, originally developed for the mass production of screws from bar stock, but long since used for a wide variety of parts from bar stock over a broad size range. Once set up, these machines run completely automatically. This is the multi-spindle screw machines. That is the process of screw machines. The next one is chucking machines. Chucking machines are automatic lathes designed for operation on castings, forgings, and other parts, rather than a bar stock. Mechanisms and other features are similar to those of screw machines, except for the bar feeding system. We go to the next chapter, round hole making methods. Drilling. The most common tool for drilling, a twist drill, is a rod with helical flutes and 2 or more cutting edges at the end. It is rotated about its axis and fed axially into the work. As it advances, it produces or enlarges a round hole in the workpiece. This is the drilling operation. There's boring, reaming, tapping, spot facing, countersinking, and counter boring. The first one, counter boring. Counter boring enlarges a hole for part of its depth, and usually machines a flat bottom in the enlarged portion. Flat bottom. The operation is most often performed to provide clearance for a bolt head or multi-diameter part. A multi-diameter part counter-boring tool can produce stepped counter-bores. This is the process of counter-boring operation.
Is making a hole that's designed to be used with a socket-head cap screw. Notice the end of our counter-boring tool has a pilot on it.
Counter-boring operation makes a flat bottom result. Just like this, flat bottom. Okay, so the next one is countersinking operation. Countersinking is similar to counter boring. Countersinking operations adds a chamfer at the entry end of a hole. Chamfer. A rotating cutting tool with the edge set to the angle of chamfer desired is fed into the hole and removes material at the edge. This is the difference between counter boring and countersinking result. The counter boring result is a flat bottom, and countersinking adds a chamfer at the end of a hole. This is the process.
Is a countersinking tool. 2 different things that we can do with the countersinking tool. First one is chamfering. Chamfering is just going in and breaking that edge around the top. If we go deeper with the tool, the operation is called countersinking. We'll use this for a flathead screw.
So that's how the countersinking works. The next one is reaming. Reaming is a secondary machining operation for existing holes. It can provide a more accurate diameter, improve straightness, and a smoother surface finish as it slightly enlarges the hole. Reaming can be performed on a drill press or other drilling machine and is sometimes done by hand. This is the illustration of reaming operation.
Here you will see the procedure for reaming on a lathe. For the purpose of this instructional video, reaming of a 12mm diameter hole will be demonstrated. Secure the material or chuck and set the facing tool to center height. Set the lathe for high speed. In this case, the machine is set at approximately 2000 RPM. Face the end of the material to ensure a flat surface. Note that a moderately high feed rate, approximately 0.25 millimeters per revolution, is used and no coolant is required. Maintain a high speed for center drilling. Remember to use coolant on high-speed steel tooling, such as this center drill. Note that the center drill should be drilled at a depth at least 2/3 of the chamfered length. Calculate and set the drilling speed according to the drill size. In this case, an 11.5mm drill is used at approximately 800 RPM. Once again, coolant is used on this high-speed steel drill bit. Coolant should be delivered via the lathe's coolant hose. However, for the purpose of this instructional video, an alternate delivery method was used. When reaming, use a coolant with high lubricating properties.
Now this is the
and
reaming
has
operation.
material requirements. Calculate and set the reaming speed according to the reamer size. In this case, a 12mm reamer is used at approximately 500 RPM. Swerve should be able to be clear to prevent the machine surface from scoring.
Now that is the reaming operation work. The next one is boring. Boring operation enlarges and improves the accuracy of an existing hose. Either the work or the cutting tool rotates about the center axis of the hole. So this is the workpiece and this is the boring tool. It enlarges an existing hose. This is the hose. This is the workpiece and this is the boring tool. It is enlarging the hose from the inside. The next one is gun drilling. Gun drilling is a rotating single flute drill, normally carbide tipped. Is guided by a bushing at the start of the drilled hole, and is self-guided thereafter by a bearing surface opposite the cutting edge. Sharpening. Sharpening makes a circular groove in a workpiece through the use of one or more cutters, or cutting teeth, rotating about a central axis. The process is used primarily for large shallow holes. It is also used to machine round discs from flat stock. This is the illustration of the sharpening operation. Multiple spindle drilling. When production quantities are sufficiently large, it may be justifiable to construct a drilling head with a number of drills, all of which are driven from the same power source and make contact with their workpiece at the same time, drilling a number of holes simultaneously. We go to the next chapter, grinding and abrasive machining. The first one is cylindrical grinding. Cylindrical grinding used to produce external cylindrical surfaces by removing material, creating smoother surfaces and providing more precise dimensions. The grinding wheel moves toward the workpiece to contact it, and away from the workpiece after the grinding is complete. This is center-type cylindrical grinding. Center-type cylindrical grinding is performed on a lathe-like machines. The workpiece is usually held at each end on pointed centers and is rotated about these centers. Now this one is a through-feed centerless grinding. Through-feed centerless grinding, a process for machining cylindrical surfaces wherein the workpiece is not held between centers or in a chuck. Instead, the work is supported by a work rest plate at the correct height and contained between two wheels. This is the process of cylindrical grinding. This is the grinding tool. The next one is internal grinding. Internal grinding process for finish machining existing round holes. It normally is performed on a lathe-like machine. The workpiece is held in a chuck or faceplate holding fixture and rotated about the axis of the hole to be ground. Surface grinding. Surface grinding moves the workpiece in a horizontal plane so that it passes under a revolving grinding wheel which contacts it and removes surface material. The result is a part with a flat, smooth surface and an accurate thickness or height. This is the surface grinding. And this is the video of the process surface grinding. So the next one is jig grinding. Jig grinder is a precision vertical spindle machine, similar to a jig borer. It is used for internal grinding. It has horizontal table that can be moved and located very accurately. The machine is used for finish grinding of hardened dies, molds, jigs, and fixtures. Low stress grinding. Low stress grinding is a variation of conventional grinding in which the objective is to minimize stresses developed in the workpiece by the grinding operation. The process is applicable when the part to be ground is subject to high stresses in use or is susceptible to damage from heat. The next one is plunge grinding. Plunge grinding is a center-type grinding operation where there is no transverse feed of the grinding wheel. Instead, the wheel is fed directly into the work. If the wheel is dressed with a form and if the width of the ground area is no more than the width of the wheel, the operation can be referred to plunge grinding. The next one is disc grinding. Disc grinding producing flat surfaces. The workpiece is held against the flat side of a large rotating abrasive disc. This operation can be performed manually when dimensional requirements for the part are not severed. Double disc grinders are used in the production of automotive connecting rods, disc brake rotors, compressor vanes, and cast iron rocker arms. This is the double disc grinding wheel, and this is the workpiece. Next one is abrasive belt grinding. Abrasive belt grinding uses an abrasive coated cloth belt to remove metal. The endless belt runs between the drive wheel and the contact wheel, and the workpiece bears against the belt at the contact wheel. The abrasive grains on the belt are arranged with orientation and spacing to optimize metal removal rates. Lubricants may be used to facilitate this operation. This is the process of abrasive belt grinding. And this is the machine of this process. This is the process. It's done manually. This is the result of the abrasive belt grinding. We go to the next one, abrasive jet machining. Abrasive jet machining, or AJM, provides cutting action from the effect of finely powdered abrasive in a high velocity stream of gas. This can be done by hand for rough cuts, stripping, or deburring. The process can be used for drilling, cutting, etching, trimming, cleaning, and deburring operations on a variety of metals and non-metals, especially hard and fragile materials. That's how abrasive jet machining works. The next one is abrasive flow machining. Abrasive flow machining, or AFM, uses a viscous putty-like abrasive medium which is pumped so that it flows against the workpiece. The abrasive particles in the medium rub against the workpiece, gently removing surface material. The process is used to run sharp corners, finish edges, polish surfaces, and remove burrs. This is the process of the abrasive flow machining. And this is the medium that the process used. It grinds inside the material. So the next one is ultrasonic machining. Ultrasonic machining utilizes an abrasive in a water slurry and a shaped tool. With the abrasive between the tool and the workpiece, the tool is vibrated at ultrasonic frequency. The vibration of the tool drives the abrasive particles against the workpiece, cutting a cavity that has the same shape as the tool. Material removal rates are low, but there are no heat effects, no burrs, and surface stresses are low. This is the simulation of the ultrasonic machining. This is the tool and this is the workpiece. And that's how ultrasonic machining works.